you for joining our webinar today. Hopefully everyone can hear me now. But our webinar today on designing polymer components for thermal environments I wanted to say that this is really born out of and motivated by conversations that I have had with clients over the past several years of my time here at Verist, kind of giving the same or similar kind of explanations about how different say interesting behavior is more relevant for polymers than it is for other sorts of engineering materials, and that way so something that is not some different things that are maybe not as widely known as I feel like they should be. And so after kind of giving the same explanations, running through kind of similar problems with various clients over the years, we thought we'd try and put this out as kind of a more broadly and more generically as a sort of webinar format to try and disseminate this information as widely as we can. And before we go too much further, I do want to say that if you have a question at any time, please use the Q&A feature in Teams. There's both the chat and the Q&A. I find the Q&A just tends to work a little bit better. I will try to answer those as they come up, but that's not, of course, always possible. So if when you type your question in, could you just reference a slide number and just say, sort of on slide 15, I have such and such question. That'll help if if I come back to it later, we can go back and I make sure I try and understand, what your question is as best I can. With that, I think let's go ahead and get started. So just by way of background to both myself and to Verist Engineering. Verist, we are a consulting firm. We offer engineering consulting services to clients facing primarily R&D and production manufacturing challenges. Have expertise in a kind of a wide array of different fields, kind of ranging from advanced computational simulations, including fluid dynamics, heat transfer, and structural mechanics, finite element simulations. We have a particular subspecialty in modeling polymers because it's my own personal bias. I think they're more interesting than other materials, but they have more interesting kind of nonlinear, temperature dependent, as we're going to talk about today, behaviors that are simply not as strongly present in other sorts of classical engineering materials. My own background, I have a PhD in material science and engineering from MIT. I've been working at Verist for just about, not quite 7 years now, as a consultant, working with clients in various spaces, including medical devices, consumer products, heavy industry, kind of especially focusing around things like advanced materials characterization, focusing around polymers, materials engineering, accelerated lifetime testing, and things like that, as well as a lot of work on adhesives and adhesive joints. So you're going to see kind of all those sorts of different influences come through today as we try and go through as we go through our webinar today. And so just to kind of set the stage, you've probably seen this already when you signed up for the webinar, but our kind of learning objectives are, to try and understand the kind of why polymers are temperature sensitive, and then some of the attributes of the actual polymer structure that caused, say, improved or worse temperature performance, sort of comparing different kind of classes of polymer materials, and so the structural elements that explain why they might have better temperature resistance, however we're defining that. We're going to focus on specifically the glass transition because this is the topic that I find that comes up most often when I'm talking to clients is there are misunderstandings, misconceptions, or just simply a lack of knowledge, frankly, about what the glass transition is and what it really means and how to kind of understand how the glass transition affects your actual product use, temperature windows or lifetime, things like that. And we're going to talk about some failure modes like creep, melting, and degradation, and sort of how to test for those and how to compare different materials to sort of assess whether or not that's going to be a prominent failure mode for your particular design. So there we go. And so the kind of more specific outline, kind of based on those learning objectives, We're going to start with sort of an introduction to polymer structure. So if you've been following along with the Barrister webinar series, you know that earlier this year I gave a kind of a much deeper dive into kind of polymer structure and characterization. So we're going to talk about that. That's going to be a little bit of a repeat if you came to my previous webinar. We'll talk a little bit about some specific failure modes to anticipate at elevated temperatures. And then we're going to go into sort of characterizing polymer thermal behavior. There are 4 techniques down here that I think are primarily relevant for polymer materials. And then finally, we're going to spend a bit of time just focusing on the glass transition because I think it is more counterintuitive essentially than some of the other things. And so I want to spend some time focusing on that as well. All right, so just to give a very high level overview of polymer structure, we kind of take this word polymer and break it down into its 2 components, poly and mer, which means many parts. And so the kind of way to think about the structure of polymer materials is that they are these long sort of strings of repeat units called monomers that are joined together by chemical bonds. And so this is experiment that maybe you did even in something like high school. It's a very common sort of demonstration for polymers, and polymerization is to essentially make nylon from a diacid and a diamine. So essentially you have a solution with this molecule, you have a solution with one of these diamine molecules, you mix them together and they form a chemical bond between the acid and the amine, and they do that sort of back to back to back to back to back, and you get this very, very long sort of chain molecule called a polymer. And so this kind of demonstration, you see a sort of screenshot or an image of it over on the right, where you mix the fluids of these 2 ingredients, these 2 chemicals, and create the actual nylon polymer that you can then sort of draw out of the solution. So you take these 2 liquid precursors, and because they polymerize, they form these very large molecules, they turn into a solid. And just to give you kind of a rough sense of scale, most polymers have a molecular weight somewhere between 10 to the 4 and 10 to the 6 grams per mole. There are, of course, many exceptions to that rule. That's really just kind of a rough estimate of how big these molecules are. So they can be very, 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 very large. And that sort of high molecular weight is really, that long chain is really what gives them their interesting properties and kind of why we like them. And so I want to talk a little bit about what I like to call the spaghetti structure of polymer materials. I think it's kind of the most useful framework for understanding the sort of arrangement of these polymer chains, where you basically you have these really, really long molecules, and they're all kind of tangled together. For the most part, with some exceptions, they are kind of in this sort of spaghetti mess within the material, sort of on a molecular scale. And this, mental map, this framework, this idea is really useful for, kind of explaining or understanding how the structure drives kind of relationships within polymers. It's just a really good kind of picture and way of understanding things. But I like to think about, kind of from a very high level, most polymer behavior that we kind of care about, especially mechanical behavior, can be explained by the answer to 2 questions, which is 1, in my particular polymer, how easily can those chains move? How mobile are they? And number 2 is, how far can those chains stretch? How far can I pull them before they break, before they're limited by sort of some other sort of interaction, either with other polymer chains or with something else kind of, inside the material. And so what we really need to talk about, especially when we think about the temperature dependence and thermal properties of polymers, is this difference between thermoplastics and thermosets. And so thermoplastics are essentially entangled polymer chains. So you have these very long molecules. When you make this sort of spaghetti structure, they're all looped over and folded over one another. And so the kind of formal word for that is entangled, but it really is this kind of spaghetti mess of long chain molecules. But the important distinction, or the important thing to remember, is that those long molecules are not chemically bonded to one another. It means that if you take one of those polymer chains and you were able to just pull on just that chain, you'd eventually be able to pull it all the way out without breaking any chemical bonds. Now, in contrast, and I should say what that gives us is kind of the key property of thermoplastics. The reason they're so useful in various industrial applications is because you can heat them up and they will soften or melt essentially, and you can reshape them. So that's why they're so good for things like injection molding or extrusion, because you take your granules, your resin, and you feed it through your extruder, it heats it up, melts it, everything, turns into essentially a fluid. You form it into the shape that you want and cool it, and you're sort of locking everything in place. But if you want to essentially rework those materials in some way, you can heat them back up again, they'll melt, you can freeze them again. You can sort of do that in some sense as long as you can. Of course, there's some trade-offs with that. But things like polyethylene, ABS, polycarbonate, and nylon, those are sort of classic engineering thermoplastics. The reason they're used in so many products is because just processing and handling them at kind of modern manufacturing scale is so much easier and cheaper. Now, in contrast to thermoplastics, thermosets are fully cross-linked polymer chains. So this is where those long chain molecules have chemical bonds, sort of these indicated here by the sort of black circles, actually binding all of the long molecules together. So that really prevents, essentially, and hinders the relative motion of those polymer chains. If you picked one of these polymer chains, say this one right here, and pulled on it, you couldn't pull it all the way out of the network without breaking some of these chemical bonds. And so what that means is that those chains can't move as far, right? So that really limits the chain sort of motion, which changes how they respond to things like a mechanical stress. And now, importantly, those bonds will not break generally upon heating. And the material kind of never really fully melts. So once you trigger that chemical reaction to cross-link your material, to bind those polymer chains together, that's it. So good examples of thermosets are things like epoxies or MMA adhesives, and actually most sort of conventional elastomers, rubbers are thermosets as well, meaning that if you heat it up, it's not going to melt, it's not going to turn into a liquid, you just sort of get a softer solid. And so you can't really reshape a thermoset in the same way that you can a thermoplastic. Now I'll talk a little bit about crystallinity, because this has really real importance for temperature dependence as well. That spaghetti kind of mess structure picture of polymers is applicable to is a good mental model, but there are actually some polymers that have regions where the polymer chains are well ordered. It's not quite that random spaghetti structure. You can see in this sort of cartoon image that we have these, let's call them the spaghetti amorphous regions, is what they're called, but highlighted in blue here are regions where those polymer chains are actually kind of well lined up next to each other. So we call those crystalline domains or crystalline regions within a polymer. And so those impart kind of greater mechanical properties to the polymer because you have more densely packed, well-ordered polymer chains. And so the key thing to remember is that all polymers contain amorphous regions, but only some polymers contain crystalline domains. And so we call them semi-crystalline polymers. And so examples of that are polyethylene or HDPE, nylon, and polypropylene. There are a great many examples, and they vary widely essentially in terms of how much of the polymer is crystallized versus how much is amorphous. You can go from even just having a few percent crystallinity all the way up to very, very high percentages of crystallinity. But the actual degree of crystallinity within even a sort of family of materials can vary quite a bit because it depends on the actual sort of polymer chain chemistry, any additives that you put in, as well as the actual strain history. So if you stretch most polymer materials, if you go far enough, you can actually trigger crystallization because you're sort of aligning the polymer chains. So kind of within all these different material families, the degree of crystallinity can vary pretty substantially. And I'm going to briefly touch on the glass transition temperature here. We're going to kind of go back into more of the effects later in the webinar, but this really applies to the amorphous domains of the polymer, because the amorphous domains at low temperatures are what we call glassy. Essentially, the low temperature has caused those chains to not be able to move very easily. So instead of sliding over one another as they do at higher temperatures, they are kind of frozen in place in some way, but not in the sort of ordered state of a crystalline domain. They really still are amorphous, but it's just very difficult for them to move. In contrast, at high temperatures, we call those domains rubbery. That sort of allows those polymer chains to slide past one another with relative ease, and gives you that sort of more elastomeric response. And so the sort of boundary between the glassy domain and the rubbery domain is a temperature that we call the glass transition temperature. And so it is tempting and relatively, a useful heuristic to think of it similar to a melting temperature. There's some thermodynamic reasons why that's not technically the case, but it is really the boundary between where you have a sort of hard material and a much more soft and flexible material, and it's the temperature that sort of defines that that transition. I just want to think about, about like sort of the mechanical properties of polymers, kind of under different, structural, have these different structural components. So I'm showing here on this slide is a stress versus strain plot for 3 different materials that have different glass transition temperatures and different, sort of states of crystallinity. So at the bottom, I'll start at the bottom. This is for EPDM, so that's very common elastomer rubber material. And these tests are all at room temperature. And so the EPDM has a glass transition temperature of negative 54 degrees Celsius. So when we do this test at room temperature, we are well above TG, meaning that we should expect those amorphous domains to be rubbery. And so that's what gives this EPDM its sort of relatively low modulus. It's sort of rubbery hand feel and things like that. But in contrast, compare that to the blue line, which is polyethylene. So that's a semi-crystalline material. It has a glass transition temperature that's even lower than EPDM. It's about minus 100 degrees Celsius. But we have a much higher modulus. The stress strain curve is much steeper at low strains. And we have this kind of extended draw region that you expect from something like polyethylene, where you have this kind of very large strain to failure, which is kind of one of the reasons we like polyethylene, especially HDPE, so much. So this is essentially, one way to think about this is essentially what those crystalline domains are doing, is that they're increasing the sort of apparent yield strength of the polyethylene. They're increasing the modulus, much higher than they would, for the EPDM, which has essentially no crystalline domains to reinforce it in the same way that polyethylene does. Now, compare both of those against this stress strain curve from PEEK, which is most fundamentally a glassy thermoplastic, which has a very high glass transition temperature around 140 degrees Celsius. And so the modulus is even higher than polyethylene. The strength is much higher, but it fails at a much lower strain. It's sort of common behavior for glassy thermoplastics is that, because those polymer chains can't move very fast, when you try and stretch them, they sort of they can't move very far before they break because of sort of the dynamics of the system. So thinking about sort of glassy versus a more rubbery domains and the crystallinity of these 3 different materials, essentially get these 3 very different responses with different combinations of those different properties. So I like kind of showing this type of behavior because it shows kind of the variety of mechanical response that you expect from these different polymer materials, and then sort of linking that back to the sort of whether they're glassy, whether they're semicrystalline, or whether they're rubbery. And so, I think a question you might ask is sort of like, if I have a material, what are ways that I can sort of change its mechanical response, at different temperatures? And I like to highlight the presence of inorganic fillers. This is an extremely common strategy for trying to create polymer materials that have better mechanical properties at elevated temperatures. And so, typically when we add inorganic fillers, typically, carbon black, carbon fiber, or glass, short glass fibers to a thermoplastic, it still retains its sort of injection moldability or its sort of thermoplastic nature, but you get a much sort of improved response at higher temperatures because those inorganic materials are essentially, the properties are unchanged with respect to temperature. And so just to see how that works sort of in practice, these stress strain curves are both from nylon material, but the blue curve is from an unfilled nylon material, and this orange curve is for a nylon material that has 30% glass fiber added to it. And I should note that the temperature these were taken at was from 100 degrees Celsius. Now, the glass transition temperature for nylon is typically about 54, between 50 and 60 degrees Celsius, depending on exactly the nylon that you have. So this response where we see this unfilled nylon measured at 100 degrees C, still below the melting point of the crystalline domains in the nylon. So we get this kind of classic thermoplastic sort of rubbery, semi-crystalline thermoplastic response with a yield stress around 25, 30 megapascals. When we add those glass fibers, the modulus is increased pretty substantially, and the apparent yield stress is probably about 3.5 to 4 times, maybe even 5 times higher. And so when we add these inorganic fillers to materials, that's sort of one strategy to use to sort of improve that temperature resistance, sort of elevated temperature properties of the material. Let's talk a little bit more about various failure modes, sort of what to expect and what they can cause. And so I like to think of these and break them down into kind of 3 different buckets. We're going to talk about each one of these sort of in turn. So on the left, we've talked about this a little bit already, but phase transitions, that's melting. Devitrification, that's when you have a glassy material and it goes through its glass transition temperature, becomes rubbery, or just general sort of softening, the sort of general temperature dependence of the material properties. Then we're going to talk just very briefly about chemical breakdown. So sort of at elevated temperatures, you can get molecular degradation, oxidation, sort of low molecular weight components of your material can volatilize and off-gas. And then lastly, we're going to talk a little bit more about permanent deformation, which tends to be a little bit more relevant for polymer materials, especially at elevated temperatures. So that's creep and compression set. And sorry, I see there's a question. Someone asked, are inorganic fillers possible to add only to thermoplastic polymers? No, of course not. You can have you can add inorganic fillers to thermosets. That's a very common strategy for thermosets as well. So I'll talk a little bit about a little bit more detail about phase transitions, or what to expect from different materials. We talked a bit about the glass transition temperature already, but this is a curve of the modulus of a nylon material versus temperature. And what I want to point out is that you can get pretty substantial changes in the properties of the material, even below the sort of nominal temperature, whether that's the glass transition temperature or the melting temperature. So if we look at this curve, between very low temperatures and about 50, let's call this about 50 degrees Celsius, you do have a pretty significant dependence of the modulus on temperature, but it's much higher above the glass transition temperature. So once we get those rubbery domains, they're essentially more temperature dependent. So even if this is kind of the state you want your material to be in, it's going to be more sensitive to fluctuations or changes in the temperature. Even as we approach the melting point, which for these nylons is around 200 degrees Celsius, and you can the data that we showed in the previous slide, where you still have a pretty pretty high strength, about 25 megapascals at 100 C for an unfilled nylon. As you increase the temperature, that modulus is going to keep going down. And this is a log scale. So this is going to actually, essentially, in sort of relative terms, could be pretty significant depending on your application. And so it's something to really think about when you are designing a component that's going to be exposed to elevated temperature, is sort of how sensitive your design is to changes in the modulus of the material. Because if this modulus is right around 200 megapascals, right around 100 C, if it drops down to 150 megapascals, somewhere around 150 C, is that going to be dangerous for your part or your design, or is it going to be acceptable? And so understanding sort of how your modulus depends on temperature is a really useful way to try and understand what kind of risks you'll see, risks you're exposing your part or your design to as as it experiences fluctuations in temperature. And this curve, this sort of modulus versus temperature curve, is actually very straightforward to measure with DMA. And so this is something we recommend quite consistently, is to just get this modulus versus temperature curve to really understand how your material kind of responds to changes in temperature. So chemical breakdown is another sort of category that we discussed. And so at relatively high temperatures, the polymer chains will actually chemically break down. So instead of they start out these very long molecules, and they'll start to undergo sort of chain scission events, different chemical reactions that will cause those long molecules to become shorter. And generally speaking, the shorter the molecules become, the worse they're going to perform. They have lower strength. They're going to be much less ductile. They're going to be more prone to sort of other sorts of time-dependent failure modes and fracture and things like that. So it is not common for polymers to reach very high temperatures that cause quick, instantaneous degradation, but more subtle degradation can occur at moderate temperatures over long time. So if you kind of expect your design to be in the field for several years, exposed to elevated temperatures or other degradation modes like UV light or hazardous reactive chemicals, over those years, even at lower temperatures, you can cause loss of molecular weight in your polymer, and therefore sort of like loss of those nice properties that it started with. So one way you can try and test for that to begin with is to use excuse me, sort of like slightly accelerated do accelerated aging studies to basically test whether or not your part, component, or your material is going to significantly change its properties kind of over your lifetime, use an elevated temperature to sort of quote unquote accelerate time. And sort of the guideline that's typically given for those types of accelerated life tests is that chemical reactions tend to accelerate by about a factor of 2 for every 10 degrees Celsius increase in the temperature. So if you increase by 10 degrees and test it for 6 months, that's approximately equivalent to testing at 10 degrees lower and testing it for a year. And so you can sort of weigh how much temperature budget you can have in your accelerated life test versus your material structure and your actual sort of needs to verify these different properties over time to kind of design an accelerated life testing protocol that incorporates, that will try and give you some information about how the properties of your material are actually going to change under that sort of long life in the field. And then I want to talk about permanent deformation. This is, I think, something that is extremely common with various families of polymer materials, and should be considered, I think, for essentially any polymer material, because they're so much more likely to behave essentially in non-elastically versus other engineering materials like metals and ceramics and things like that. And so the two kind of flavors of permanent deformation that we're going to talk about today are creep and compression set. Kind of fundamentally, the underlying physics are similar, but they're measured in different ways and usually kind of for different applications. So, excuse me, I kind of want to talk about them a little bit differently, because even though they're kind of effectively measuring the same thing, it's important to kind of talk about the distinction. This image that you're seeing here, this is a creep test picture that we developed, excuse me, here at Verist for, we do creep tests in this fixture typically for about a month. It's a relatively simple fixture, uses a hanging weight and some displacement transducers to measure the sort of deformation of these test samples, over long times at different temperatures and things like that. So it's a way of actually measuring the sort of creep response of these materials. So to talk about creep, so creep, is kind of definitionally occurs in materials under static loads. So you basically take a sample and place it under a constant tensile stress. The polymer material will start to deform more and more over time, right? So there's not just the elastic deformation, that sort of instantaneous elastic deformation. There is also a sort of time dependence to the deformation of the material. And most prominently for our discussion here today is that at elevated temperatures, polymers deform at higher strain rates and rupture earlier than they do at lower temperatures, because fundamentally creep is a kinetic process. Those polymer chains need to move over and across one another, and that sort of happens in a time-dependent way, much like it's almost like fluid flow, a very, very viscous fluid that's flowing very, 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 very slowly. But if you heat it up, that viscosity is going to drop, and so it's going to flow much faster. It's analogous to the sort of behavior of polymers under creep static loads. This video that's playing, this is on from one of our test fixtures. We're using what's called digital image correlation to measure the strain in these samples. But as I go back here, these tests are done at the same at the same stress, and it's the same material, but these are at 2 different temperatures. And you can see at the low temperature, we get sort of very minimal strain in the sample. It doesn't tend to increase that much over time, but at higher temperatures, we have a much faster response, a much faster creep rate, even in just a few minutes. And this is a relatively high temperature for this material. You start to see that failure, the sort of larger strains and failure in that material start to come into play. So, the way you kind of fix this from a materials point of view is by using, materials that are cross-linked thermoset materials. They tend to resist creep deformation more than thermoplastics do. Using glassy polymers, so as long as we're staying well below our glass transition temperature, you can have much better creep resistance. Or crystalline polymers, semi-crystalline polymers, with higher degrees of crystallinity. Those crystalline domains are going to creep less than the amorphous domains, so expose you to sort of less risk of creep failure, creep deformation. So compression set, this is more typically done for more elastomer materials, soft elastomers, and foams. This is a way of measuring permanent deformation under a fixed displacement, so a fixed strain rather than a fixed load. And there's a sort of a standard test for this, where you take a sample and compress it a specific amount, and then you hold it at that sort of fixed compression for some amount of time, typically 24 hours or something like that. Get the exact standard specification. And then you release and allow it to kind of recover as much of its original thickness as it can. But the actual value that you're measuring is sort of the new height of the sample relative to the old height of the sample, and that's the compression set. So just like creep measures permanent deformation in a material under a static load, compression set measures essentially the permanent deformation in a material under fixed deformation. So compression set is a little bit more common for parts that form seals, so things like gaskets, because if you have too much compression set, then it will no longer sort of maintain an effective seal, essentially, between the 2 mating surfaces that's supposed to prevent fluid flow across. And so in our case, and for this webinar specifically, concerned about elevated temperature, because again, this is a kinetic process, right? We're compressing the material, we're getting some stress relaxation. Essentially, that stress is going to decay over time. The process is accelerated by elevated temperature. And so, most kind of elastomers, gaskets, things like that will, publish data sheets about their parts that include measurements of the compression set of the material. But that may only be taken at, let's say, room temperature. And if you need to use it, use the material, use the gasket at an elevated temperature, then I think it's, in my opinion, it's very important to actually characterize the compression set at a temperature that is sort of relevant to your application. And so I think for the next section, we're going to talk about characterization. So we've gone through you've seen some examples of this already. There are a few more that we're going to talk about kind of in more detail. The first one I like to talk about is called dynamic mechanical analysis, or DMA. So this is kind of fundamentally a mechanical test of a polymer material, but I like to think of it as more of a thermal characterization, because we're measuring mechanical property, but this sort of hood that you can see here, and this is a picture of the DMA that we have in our lab, kind of comes all the way down and sits on top of the fixture and has sort of a high-powered convection oven. And so what we get is very precise temperature control of the material while we're measuring its mechanical properties. There are a couple of different ways, kind of ways that are of measuring mechanical properties that are conventionally done with the DMA. One is to do oscillatory deformation, meaning we apply a sinusoidal strain to the material and measure what's called the dynamic moduli, storage and the loss modulus as a function of frequency. You can apply a step strain and get the relaxation modulus. That's essentially spiritually similar to the compression set test that we just discussed, or a step stress to measure the creep properties of materials. So you apply a constant stress and measure the strain as a function of time. And I'm showing this here in tension because I think it's kind of the most straightforward to understand. You can get different test fixtures for the DMA for compression or cantilever bending or 3-point bending or something like that. Kind of depends on the actual needs of the specimen and the type of testing that we need to do. But the going back to the DMA test that I kind of recommend to essentially everyone, if you are designing a product, a component with some sort of polymer that has is going to be exposed to, even a reasonably or even a small increase in temperature or decrease in temperature, I strongly recommend getting a temperature sweep done on a DMA. And the reason I recommend that is because this is all from a single test, and we get so much information about both the structure of the material and how it responds to elevated temperature. So what we do in a temperature sweep is we take, the sample of the material, whether it's in tension or bending, doesn't really matter, and apply that sinusoidal deformation to the material. We're going to measure the storage modulus. You can think of that as being roughly equivalent to the Young's modulus of the material. And the loss modulus, which is essentially a measure of energy dissipation in the material. So essentially viscous losses within the material. And you can see how these change versus temperature. And again, this is a nylon 12 curve that we were looking at before. Now I'm showing it with the loss modulus. And you can measure a couple of things about your material. You can measure the glass transition temperature. You can either, there are different ways of actually like picking out the number for TG. You can use the storage modulus. You can use the loss modulus. I tend to prefer the storage modulus because this is sort of like the functional property that we typically care about, the stiffness of the material. You can also see the melting point here. But even, kind of whether, you're picking out these numbers specifically or not, what you really get and the real value from this temperature sweep is just the modulus as a function of temperature, right? Which tells you that at a temperature of 50 degrees, we expect our modulus to be about, a little bit less than 2 gigapascals. And then at, minus 50 degrees, it's going to increase a little bit. It's going to be, not quite 3 GPa. And whether that is, kind of that difference is relevant for your application or not is part of your analysis. But that once you hit about 50 degrees C, as soon as you go above that, because you're hitting this TG range, you're going to have a steep drop off. This is in log scale again. Of the modulus. And so once you hit that temperature, you're going to have a much softer material. And this is all done through just one single test. It's relatively easy and straightforward to perform, and you get so much information out of it. It's just the most informative test you can do to characterize sort of the temperature like behavior of your materials. Let's see, I see someone had a question. Why don't resin manufacturers provide these temperature sweeps on the data sheets? That's a great question. I don't know. I'm sure it comes down to something about their internal needs, whether they think that the sort of the value is there for them, in terms of their communication with their clients. And the flip side of that is I have seen curves like this on data sheets before. I would say they're not common. It's probably closer to 1 in 100 data sheets than it is anything else, but they do exist. And I would also say, ask your material suppliers because they may have this information. They may just not want to put it on the data sheet could be a quite a variety of reasons. But I would just say ask, and maybe about half the time that they're willing to share, or they have one that they're willing to share. But good question. And so before we move on from the DMA, I want to very briefly highlight something, sort of an advanced DMA method. It's called time temperature superposition. And so using a DMA, it's most commonly done with a DMA. We do this process where we use elevated temperatures to forecast the creep performance of a material over essentially very long periods of time. And so this is kind of using the idea that the creep deformation in a material is a kinetic process. And so like any other sort of kinetic process, if we increase the temperature, we make that process happen faster. So what you can see here is over on the left, I've done successive sort of creep tests on this epoxy material at 30, 40, and 50 degrees Celsius. These lasted only 30 minutes each. But this sort of process of TTS, we shift these curves along the time axis until we get this sort of self-similar master curve. You can see the results, the green 30 degrees C, the orange 40 degrees C, and the purple 50 degrees C. Sort of when you shift them along the time axis, you get this sort of self-similar curve that we call the master curve. And so using this process, we're able to kind of extrapolate out to about 2 years at room temperature, how much strain we're going to get in the material. And so this is kind of a more advanced CMA method. I like to bring it up because it is very powerful. There are a lot of sort of trade-offs of using it, and sort of questions you need to ask before you just sort of blindly blindly believe a process like this. But it is something that we do a lot because when we're working with clients who are designing products, say this is going to be under load for 2 years or 3 years or 10 years or something like that. And so, we can't wait for 10 years to have real-time test data on this product because then we just never make the product. And so using this sort of accelerated testing, which is done within, even just a few hours, to be able to make predictions, even though, there's sort of the, it's a model of the material behavior that's going to be in some way inaccurate. But it's very helpful to try to understand, in this case, at 2 years, we're expecting about, 8% strain or something along those lines. Is that a failure for your part? Is that well within your tolerance margin? And you can sort of, the way I like to think of this is using a tactic like TTS to try to predict the long-term behavior of material, is because you sort of end up dividing things into one of 3 buckets. One is this is definitely not going to be a problem because we have so much margin that even if our TTS master curve is inaccurate, we're going to be fine anyways. The last bucket is this is definitely a problem. We're predicting way too much strain. That's definitely, our product's definitely not going to work anymore. So now we need to go back to the drawing board, and we can avoid some sort of qualification testing or the sort of more extensive testing that we were going to do because we essentially think there's very high likelihood of failing that test. And then sort of squishy middle where maybe we're safe, but we don't have enough margin, or maybe we're not safe, but there's not much margin on the other side. So we should really rethink our design. Maybe do some more extensive testing before we fully redo our design. But that's all part of the sort of engineering design process. So yes. See a question regarding time temperature superposition for creep master curve generation. How reliable is this when compared to real-time creep test? I mean, so that's kind of the question about time temperature superposition. I found cases where it's essentially what I would say very reliable. You'll find cases certainly where it's not very reliable. And I think we're going to have a whole webinar about time temperature superposition later this year. So not to plug a webinar I'm going to give in a few months, but we're going to talk about that in more detail then. The short answer is that the simpler your material is, the more likely it is to be valid. The lower your creep stress is relative to the material's kind of effective yield strength, the more likely it is to be valid. And you can sort of interrogate the actual results you get from TTS in various ways to kind of give you some information about whether or not it's going to be valid. But the way I like to think about these is that kind of as I hinted at earlier, this is a model, and as the saying goes, all models are wrong, but some are useful. So the question is not, is this valid or not? The question is, how useful is this to us as in this part of our design? And so depending on how certain we need to be about the performance, or how risky it is for this sort of failure mode to be, we'll do the TTS testing in conjunction with real-time creep tests. And so, we get an immediate answer that allows us to maybe interrogate our design while getting that sort of longer term validation that's sort of more, that's real time, that doesn't rely on any sorts of accelerated testing. See, how would you characterize thermal interface materials that are very compliant to quantify stiffness and tension or compression? I mean, the short answer to that is that we have we have characterized thermal interface materials. It depends a little bit on what your actual use case is. Typically, when you're modeling them, they are thermal. It's assuming you're talking about TIMs that are sort of more paste-like, sort of thermal paste materials, which are typically just sort of inorganic particles dispersed in sort of a polymer, sort of carrier. It depends on how you want to analyze those. We will do sort of conventional mechanical testing on those. You are depending on how you're actually treating those in your analysis, it would change how I would test those. So the short answer is with difficulty, and by trying to understand the larger picture, which is what are we trying to get from the analysis that we're doing. But that's a good question. I do want to move on a little bit from DMA, since I do see that we have about 13 minutes left in our kind of allotted time here today. But thank you everyone for the questions. To talk about just thermomechanical analysis, so this is, I think we're only going to spend one slide on this, but TMA testing measures the coefficient of thermal expansion of your material. And the real reason I want to mention TMA is that polymers typically have much higher CTEs than metals or ceramics. But even more importantly than that is that at the glass transition temperature, there's a pretty dramatic change in the CTE. So this plot is showing the dimension change, essentially the change in length of a sample versus temperature for a polycarbonate material. This is an amorphous thermoplastic. And so below TG, you have a much lower CTE than above TG, where you have a much higher CTE. So if you have a rubbery material, you should actually expect a much higher CTE. And so that's something to think about as you're going through the analysis of your design. Where are you going to get more or less essentially thermal stress risk from your material? Is that if you are in fact going through TG, you need to take that into account in your analysis. Next, we're going to spend just one slide on TGA. This is thermogravimetric analysis. This is a relatively straightforward technique for measuring kind of the temperature, sort of elevated temperature resistance of your material. Essentially, you take a few milligrams of your material and heat it up and measure the loss in mass. And so the things that you might be concerned about for your material is the off-gassing of low molecular weight components. These are typically things like additives or plasticizers or something like that. So if you see kind of significant mass loss at lower temperatures, that sort of allows you to set an upper limit temperature for your material that maybe you wouldn't have seen in some other characterization method. This is you can do other things that with TGA, like measure solvent absorption or compare and look at inorganic fillers and things like that. But so this technique I think is rare that I actually recommend using TGA for this particular purpose, but I do want to highlight it as it is a technique that's out there. And so the technique that I want to spend a bit more time on is DSC, or differential scanning calorimetry. So this is a thermal analysis technique that is, in my opinion, extremely powerful and extremely counterintuitive to actually understand. And one of the reasons it's so powerful is that you only need a few milligrams of material. And what we're actually measuring in a DSC test looks like this, where we have basically two crucibles that we're heating at the same heating rate. One of those crucibles has a sample, and one of them is empty. What we're actually measuring during a DSC test is the difference in heat flow between the sample and the reference. And so that's why, as you'll see in the result on the plots that you get from a DSC test, the actual test result you get is usually heat flow versus temperature. It's what's used to kind of analyze these tests. And so the things that we can learn from a DSC test, from just a few milligrams of material, is the glass transition temperature. You can measure the melting point for your material. You can measure even the percentage crystallinity of your semi-crystalline material. You observe something that's called cold crystallization. We'll talk about that. And you can also measure other thermal properties of material, things like the heat capacity. It's kind of an advanced DSC method, or thermoset curing, or really any sort of chemical reaction that has an enthalpy associated with it. You're actually going to see the results of that in a DSC test. So they can allow you to help sort of set thermal budgets for, let's say, an adhesive curing process or something like that. So how do these results look? This is a figure that I grabbed kind of from the literature, but this is plotted as sort of energy flow or heat flow versus temperature. And so in most tests on polymers, what we're doing is heating the material at a constant rate. Just as an example, around 10 degrees per minute. And so this is the result that you'll get on an amorphous thermoplastic like polystyrene. And you see this little step right here, right at about 95 to 100 degrees Celsius. That's us measuring the glass transition temperature of this polystyrene material. And this is how this actually looks. And so the reason I want to show kind of a real result is that if you've never seen a DSC curve before, you might look at this and say, is that anything? Is that just noise? And the answer is no. That's what this really looks like. So what makes DSC a little bit more counterintuitive is that, this line isn't flat, otherwise it has a sort of curved baseline, but this little step here is the glass transition temperature. For semi-crystalline materials, this tends to look a lot more interesting, right? So this upper curve, this is for PET. So PET is semi-crystalline sort of by nature, but you can also see we can measure its glass transition temperature right here around 85 Celsius or something like that. And we have these two peaks in the curve. There's one sort of positive peak right here at around 125 C, and one negative peak here that's around 250 degrees C. The reason I like using PET as an example for DSC tests is because most PET, essentially that we interact with or that I interact with on a day-to-day basis, is clear. Something like a soda bottle or a drink bottle or something like that, that's clear PET, that sort of packaging material. You want it to be clear. But that PET is sort of naturally wants to crystallize. And so the way they process that PET is by melting it and cooling it super fast to sort of prevent that crystallization from happening. But if you heat that PET up slowly, once you get to a temperature where those molecules can move around more freely, they have more free volume. So once you've gone past the glass transition temperature, it will crystallize, right? Because that material actually wants to crystallize down here, but it's kinetically limited from doing so. It won't crystallize for even hundreds or millions of years. But as we increase the temperature, the PET starts to crystallize and we get this exotherm, right? So that is releasing energy. And then as we heat that PET more, we get a negative peak, which is melting. So all those crystalline domains that we created as we heated the material up, it takes extra energy to melt them. And so that's why we get this endotherm, this negative peak. And so the area under these curves is essentially proportional to the percentage of the PET that was crystallized at either crystallized or melted at this point. And so if you know the sort of intrinsic heat of melting of these materials, you can actually estimate the percentage crystallinity of a sample that you measured in DSC. And the last, I think, topic that we're going to talk about a little bit more is the glass transition. I call this, and why it will cause you headaches. Some of the results I'm showing here are from kind of actual work that we've done with clients. So we've been talking about the glass transition, kind of so far as this kind of border between the sort of hard glassy materials and flexible and soft materials. But I think one thing that I think is perhaps useful is to think about this rather than being a single number, sort of this temperature where your material softens by a lot, is that it's this actual region that spans for this particular material between about 60 degrees up to 100 degrees Celsius, where we have this very strong temperature dependence of the modulus. And so you see this drops about 2 orders of magnitude in this window, meaning that if we have a sample of this material and we want to try and measure its mechanical properties, it's going to be very sensitive to fluctuations in the temperature. Even a few degrees higher or lower will lead to factors of and sort of multipliers on the modulus, not just small deviations. And this is kind of an actual example of a test that we ran. So this is a material that we were, was being used in a device at around 10 degrees below its glass transition temperature. And so we really needed to understand how that material behaved, close to its glass transition temperature. So these two tests of the same material, the red and the blue, this is a stress versus strain curve, were done at nominally the same temperature. But whenever you're doing sort of mechanical characterization, there's going to be small fluctuations in the temperature. And so we're essentially unable to get a consistent measure of the material properties due to those fluctuations because the material is so temperature sensitive over this range. And you can see there's probably about a 3x difference in modulus and a 50% difference in the actual kind of measured strength of these material. And so if you think about that, this is under laboratory conditions, as consistent as we can get them. But if you put this part in the field and you have it at this temperature, you're going to get this kind of behavior. You're going to have some much different material, much stronger material. You're going to have some much weaker material, some much more compliant material. Is that difference going to cause failure in your device? It leads to a lot of headaches in terms of design. and sort of analyzing and designing around these types of features. And then speaking of the glass transition temperature, it is very sensitive to your material history. So this is data on an epoxy material where they measured the glass transition temperature as a function of the degree of cure. So degree of cure going to 1, which is 100%. Essentially, all of the chemical bonds in this thermoset are fully saturated. And you can see that in this sort of high cure regime, you have about a 3 degrees per percent cure. Sort of the slope is what the slope is here, meaning that this is how much your glass transition temperature changes as you change that degree of cure. And kind of going along with what we showed in the last slide, if you go from 90 to 95 to 100% cured in your material, if you look at the modulus versus temperature, you're essentially shifting where that TG is going to be, where this softening window is going to be. And so depending on where your operating temperature is, you really need to understand, is my thermoset 92% cured? Is it 97% cured? Because that is going to change what your upper limit sort of use temperature could be. Let's see. Someone asked, when is it useful to use TG instead of HGT? That is a great question. So for those that may not be familiar, HGT is the heat deflection temperature, sort of a standard way of measuring the sort of high temperature performance of materials. The way I would phrase this is that like the TG is a much more fundamental and intrinsic parameter of the material. The HGT is measured under a specific set of conditions, typically sort of a constant load, and once the deflection reaches a certain value. It's essentially, depending on your assumptions, a criterion on when the modulus of your material drops below a certain value. I forget what that value is. I think it depends on the applied load. So the sort of answer is that both can be useful, but if you can use the TG, it's going to be much more extrapolatable to other sorts of parameters. That may or may not be provided by your supplier. They may only provide the HGT because it's a little bit sort of more straightforward of a test or more consistent, depending on their setup. So that, that's kind of the distinction between those two things. So, speaking of this sort of like focus on the glass transition temperature, these are kind of my if you take nothing else away from the talk today, know what your TG is. For your materials, every material that goes in your design, you should know what the TG is of that material, even if it's just, this is EPDM, so we know it's about minus 55 C. Even if you don't measure it, if you have a good sense of it, you should know what it is relative to your expected use ranges and make sure that you're staying far away from TG if you can. My second recommendation is to measure your TG, especially most usefully with the DMA, because you get so much more functional mechanical information from a DMA temperature sweep, and it's a relatively inexpensive test to run. Measure your TG. If you have to use DSC, you only need a little bit of material. It doesn't need to be a sort of a nicely shaped tensile specimen. You can also use a CTE measurement to measure TG. That's, I think, even more difficult. I really only recommend that if you're also concerned about the CTE mismatch in your materials or something like that as part of your analysis. But if you take nothing else away, you need to know what the TGs of your materials are. Let's see. And someone asked, can you comment on the difference between TG measured with a DMA versus a TMA? Yeah, this is kind of an interesting question. With all these different methods, you're going to get slightly different results on the exact number that you get for TG measured in different ways. They're going to be within usually about 5 degrees of one another, kind of give or take. But this kind of goes along with kind of what we showed earlier, which is that that glass transition is really more of a region than a specific temperature. So even if you measure it one way and it's 50 and another way that's 55, keep your material below 35. Is going to give you more margin on that because of the sort of different results. But there's no one of those that's kind of fundamentally correct. That's the true academic correct way of doing it. It really comes down to a little bit more about the function and what you're actually doing in your application. let's see, I see another question here. With increasing temperature, there are different regimes that can induce structural changes. How do you choose the elevated test temperatures that accelerate creep and not cause a material change? I mean, the real answer to that is you have to know what your TG and melting temperature are. The other way of answering is sort of like what temperatures are relevant. You know, with something like a time temperature superposition test, it really doesn't cost us much to add additional temperatures to it. We sort of pick an upper limit temperature, and then if we find out later that data is not useful for TTS, we discard that data. So it's typically easier to generate the data first and discard it later than to sort of run the test and go back at the end and say, oh shoot, we should have done another 30 degrees or something like that. So that's typically what we'll do in those cases. Yeah, and we've gotten 3 minutes over, so thanks everyone for staying a little bit longer, and thank you everyone for joining. Just to kind of summarize what we talked about today, we talked a bit about kind of the structure of polymer materials and how polymer chains kind of affect the sort of elevated temperature performance. Talked a fair amount about the sort of different permanent deformation modes of polymer that polymers are more susceptible to than other sorts of engineering materials. And then we talked about characterizing material behavior using these different techniques, which give you different sort of windows into the high temperature stability of your materials or functionality of your materials. And finally, like I said, if you remember nothing else from today, you will have headaches if you try and use your material near your glass transition temperature. So you should know what that is, sort of beforehand. Before we sign off, I just want to plug our ongoing webinar series. We have a cadence of about 2 webinars per month that kind of span the different expertise we have here at Verist, including our simulation practice, as well as our polymer materials characterization. I think potentially relevant to our audience here today is that on August 18th, we'll have a webinar specifically about thermoforming materials. So you'll kind of recognize some of the topics that we discussed here today, but applied in a slightly different way, to how we use elevated temperature to form materials and how to best do that using different kind of methods of material characterization and simulation. And then the last thing that I want to just mention is that in addition to our sort of online free webinar series, Sean has a kind of series of paid training classes. These are much more in-depth classes, and the next one is an online class to be offered in September on advanced testing and modeling of polymers for finite element simulation. So Sean is a real expert, perhaps one of the experts in this field, about how you go from a design with different materials into a kind of a full-fledged simulation of that design or different load cases, and how you need to account for the different sort of interesting material behavior of polymers in those different situations. So with that, I think I'll sign off. Thank you everyone for the lively discussion. Great questions today. Hope to see you in our upcoming webinar soon.